Refrigeration, we're going to study the refrigeration cycle. That is, the basic cycle is Carnot cycle. Then we'll introduce VCRS. Then we introduce the various types of refrigerant and which refrigerant is suitable for which application, and we'll solve some basic problems on VCRS. Refrigeration is defined as the removal of heat from a space or a substance. If you remove from the space, it is called as air conditioner, and if you remove from the substance, it is called as refrigerator. To maintain it at a temperature lower than that of surrounding environment is called as refrigeration. This one is called as cold refrigerated space, is maintained at temperature TL. This one is warm environment. This one is QL. QL is called rate of heat removal. So QL is called as rate of heat removal or extraction. This one is W is called as work input, and QH is called as rate of heat rejection. If this device is refrigerator and your effect you want on cold space, then COP is given by is QL divided by W. If it is a Carnot model, it is a TL upon TH minus TL. And if the same effect you want to take on warm environment, it will be called as heat pump. So COP of heat pump is given by QH divided by W equals to QL plus W. So we can substitute for this, and it can be proved that the COP of heat pump is always more than COP of refrigerator by 1. The unit of refrigeration is given as 1 TR and is defined as heat required to produce 1 ton of ice per day from water at 0 degrees Celsius to ice at 0 degrees Celsius. So 1 British ton is 2240. So it will be defined like this: 1 ton, 2000 pounds. When we want to convert this, divided by 1 kg, and 1 kg of is equivalent to 2.24 pounds, and 1 day is equivalent to 24 hours is equivalent to 3600 seconds. 8, the unit of tons per day multiplied by your kilojoules per kg. Kilojoules per kg. So this approximately come out to be 3.52 kilowatts. So 3.52 is approximately equals to 211. Standard practice, 1 ton of refrigeration is taken as equals to 210. The cycle is consist of 4 processes. 1 to 2 is isentropic compression. 2 to 3 is constant temperature heat rejection. 3 to 4 is isentropic expansion, and 4 to 1 constant temperature heat absorption. Observe this graph without the dome shape, then you require 4 components only. Without dome, if I remove the dome, so we required only 4 components. One is compressor, one is heat exchanger device for rejection of heat, one is turbine for expansion process, and one is another heat exchanger for heat removal from the low space. But as soon as the dome will come, the concept will change. Now why the concept is changed? Because so if you observe this under the dome, you will find the one pressure line will be like this, one pressure line will be like this, and a third pressure line will be somewhat like the pressure is increasing from pressure P1 to pressure P2, from P2 to P3. So 1 to 2 is isentropic compression. 2 to 3, or I will say this one is additional point is 3A. 2 to 3A is isothermal compression. 3A to 3 is a constant pressure, or we can say constant temperature heat rejection. 3 to 4 is isentropic expansion. Now this time I am expanding from P3 to P1 in sequence. For expansion I required only one device, but to move from P1 to P3 I required 2 devices. One is isentropic compression, and that followed by isothermal compression. And again from 4 to 1 I required 1 heat exchanger design. So total components required are 5 as far as the TS diagram is considered. So components are like this. This device is called as evaporator. It's called as condenser. This one is a compressor but is working on isentropic process. Works on isothermal process. and this one is turbine working on isentropic process. Evaporator to compressor inlet is state 1, that is a dry and saturated vapor, else vapor only or gaseous state. From it will compress to the state equals to 2. Then further compression takes place. This one is pressure P2. Further compression takes place from 2 to 3A. So this compression takes place from 2 to 3A. This one is isothermal compression. At this point the pressure reach is P3. From P3, that is 3A to 3 is condenser process. So 3 to this condition is 3A and this point is 3. 3 to 4 is expansion process. So in this case the cycle will execute in anticlockwise direction. From the dome we can say that the process in the condenser is constant temperature as well as constant pressure. In evaporator also we have a constant temperature as well as constant pressure. Initial condition inlet to the isentropic compressor is dry and saturated. The state 2 represents the superheated vapor. A represents again dry and saturated vapor pressure. 3 represents saturated liquid condition. 4 represents the two-phase mixture. Practically it is known that this is to have run at very high speed, whereas this has to run at very low speed. So in a cyclic process, one device is running at a high speed and one device running at a low speed. So we have a reserve area. In that case only we can continue this, but it required additional space. Secondly, if you observe about the turbine and if you observe about the compressor, I have a little discussion on this one. In TS plot, this one is low pressure, high pressure. 1 to 2 represents isentropic compression, and the work required for this one is Cp minus T1. Point 1 represents entry to the compressor. If you want that machine should require less work, then will you shift this curve on the left hand side? So what is the objective when you design for compressor? Is the inlet to the compressor should be as small as possible. Agree? So instead of having a compressor at this point, and if we have a compressor at this point, if I call this one is 3 and 4, so is the work required for this compressor is always lower than this one. Whenever you design any system in thermodynamics, and if you are entry to the compressor, then you always desire the entry point to the compressor should be as small as possible, because you are knowing this fact. As you move towards the leftward side, the gap is closing. And if the gap is closing, the difference between T2 and T1 or higher difference between higher temperature and lower temperature is go on decreasing. And it means that the work required will be less. Now same thing, but exactly opposite manner will be applicable for turbine. So 5 to 6 is isentropic expansion. This time the work produced will be T5 minus T6 multiplied by specific heat. And this drop will go on increasing as you move towards the right side. So if we have the entry point equal to 7 and exit point equal to 8, then the turbine is more useful. So turbine is more useful if the entry point of turbine is at higher temperature. The compressor is more useful if the entry point is what? Low temperature. Turbine and compressor, they are working exactly opposite. So whenever you design any machine, turbine power plant or gas turbine power plant or steam turbine power plant or refrigeration, you always keep in mind if the device comes in compressor, the entry to the compressor should be kept as small as possible at temperature, and the turbine should be made at high temperature. This is applicable for the ideal gases as well as this concept applicable for the vapor system also. So conclusion is that if we have these two process for compressor, avoid this. If you have these two process, then avoid this. And if you are at this point and if you make a certain heat addition, that is always welcome. And if you are at this point and you want to compress it, it is always welcome that you should cool the liquid. So before compressor we always cool. and before entry to the turbine we always heat. But if I say that my turbine is operating on this side, then is it any meaning on this one? If the turbine is operating on this side, is this quantity of work produced is very, very small. Now check this compressed turbine. Is this turbine is operating on low temperature side. This turbine is operating on low temperature side. Even this turbine will produce the work, is the work produced by this turbine as compared to this turbine, and this turbine is negligible. So even this is a negligible quantity. So Carnot has suggested that we should use the turbine, but the work produced by this turbine is useless because you are using it on what? Lower side. We should use it on the higher side. So this work produced is almost equal to what? Negligible, is not sufficient to drive these two compressors. And therefore extra work is always required, will be supplied to these two. So net work always required. Even you have an expander, even we have an expander, this expander is not going to produce that much amount of work which is sufficient to drive the compressor because we are working on low temperature side. So the work produced for this one is negligible. Whereas compressor, are we working on the higher side? So the work demand is increasing and the work produced by the system is less. So the net work required will be higher. So this cycle is not possible because of these two. So either you have to eliminate this or you have to eliminate this. Second drawback of this one is not producing any type of work except is expanding from high pressure to low pressure. Since we are not generating any type of work, we'll remove this component. Instead of this, we'll add the throttling device, whose function is also expansion process. And then this one and this one. Out of that, this is making a more trouble because it is working at low speed. So we'll eliminate this. We'll keep with this. That is in our new system, we have a evaporator, we have a isentropic compressor, we have a condenser, and instead of this device, we have the throttling device. That is the expansion device. Then that cycle is called as VCRS, and this hurdle has overcome. So is VCRS is a more practicable cycle. So we have one device is called as evaporator, device is called as condenser. From Carnot we reject isothermal compressor and we allow isentropic compression, and no work is produced by this device or negligible work is produced by the device is replaced by valve. Cooling is carried out at constant enthalpy. This one is carried out at constant temperature, constant pressure. This one is also carried out at constant temperature and constant pressure. The condition at inlet to the evaporator by default is always dry and saturated, and the condition at of condenser and entry to throttling is always saturated liquid condition. If nothing is mentioned, you can assume entry to compressor dry and saturated, and entry to throttling is saturated liquid. From refrigerator space is maintained at temperature lower than atmospheric temperature. So some heat will leak from this side. Whatever the heat is leaked from this side is continuously absorbed by evaporator. Maintain the temperature of this space at a temperature lower than atmosphere. And condenser will reject this heat back to atmosphere. This one is QH. No work is produced during the throttling and some work is required for driving the compressor. We have two pressure only. One is called as evaporator pressure and one is called as condenser. The entry to the point 1 is dry and saturated. 1 to 2 is isentropic compression. 2 to 3 is a constant pressure cooling. So temperature we are not maintaining constant, but pressure we are keeping constant. So from 3 to 4 we have a expansion, and this is an irreversible process during which the entropy will going to increase. So this one is 4, and from 4 to 1 we have a constant pressure as well as constant temperature, but we call this as constant pressure process. We call this as constant pressure process. This one is isentropic process and this one is isoenthalpic process. So VCRS has 4 processes: isentropic, followed by constant pressure, followed by isoenthalpic, followed by constant pressure process. Now we want to make a comparison between this cycle and this cycle. Now, what are the disadvantages that we are coming from the VCRS with respect to Carnot? First of all, we'll make this zone here and we'll show this zone here. So this zone is called as superheated horn, present in the case of Carnot cycle, but is present in the case of VCRS. So this one represents the extra compressor work. Previous work was only 1, 2, 3A, and now the work is 1, 2 and this portion. So the work done will be increased. This is extra work. COP is defined as QL divided by W, and rather this one is W net as per the previous case is concerned. So this one is extra work. One difference between these two. Second thing is that we have the refrigeration effect is from H1 to H4 in this case, which was this region, and in this region the refrigeration effect is this quantity, that is the QL quantity. Quantity in a Carnot cycle is from H1 to H4. So RE for this one is H1. So this one is the extra refitting effect taking place in the case of Carnot. So this is a loss of refitting effect. So denominator has increased, numerator has decreased. So overall COP of this system, that is VCRS, is always lower than the Carnot cycle. Two reasons. In the previous case we are using the expander. Whatever the quantity of the work produced by the expander will always decrease the net work input. In this case we are not using any type of expander, so this quantity is representing the loss in work, and this quantity is not at all produced in this. So your W net is further increased in the case of VCRS. So there are three disadvantages of VCRS over Carnot. First is extra work of compressor, second is loss in RE, and third is loss of expander work. So COP of VCRS is always lower than COP of Carnot. For dynamic analysis of VCRS system, all devices are working on steady flow, changes in kinetic energy and potential energy can be written as Q plus HI equals to W plus HE. We apply this equation to the compressor. Compressor is isentropic, so Q is equal to 0. The process is taking place from 1 to 2. HI is H1 equals to W12. HE is 2. So W12 is, if you see this TS plot, 2 is the superheated, 1 is dry and saturated. So naturally enthalpy at point number 2 is more than 1. So this quantity is negative. One is work supplied to compressor. So when we say work supplied to compressor, we write WC, and therefore this quantity is H2 minus H1. General formula always work fine, higher minus lower value. The second component we have is condenser. In condenser the heat is rejected out is 2,3 plus H2 is equals to no work done in the condenser 0 plus H3. So Q23 is equals to H3 minus H2. H3 is the enthalpy of saturated liquid and H2 is the enthalpy of vapor, superheated vapor. So H3 is always lower than H2. So this quantity is negative. It's Q out. We called it as QH is H2 minus H3. It is called as heating effect. Then the next device is a throttling device. For the throttling device, it is known that the work done will be equals to 0, no heat transfer. So there is no point in throttling device, but still I write H3 equals to H4. Now number of times they will ask you what is the dryness fraction at point number 4. So is at this point number 3 is H3 equals to HF. Is it at condenser pressure? Point number 4 is a wet point. So it has an enthalpy of HF plus X4 HFG, which is written as Hg, minus HF you have to take at evaporator pressure. Solve this, we can find out dryness fraction at the end of throttling. And the last device is called as evaporator. The entry to evaporator is 4. So we have Q41 plus H4. There are no moving part in evaporator, so this equals to 0 plus exit enthalpy is 1, that is H1. So Q41 is H1. H1 is more because it is a dry and saturated, and 4 is, so this is always a positive quantity. Positive quantity means that heat is absorbed. So heat is absorbed, we'll write this as QL. It's called as a refrigerating effect. So power required to drive the compressor is given by W dot C is equals to m dot of refrigerant multiplied by H2 minus H1. A refrigerating capacity is represented by RC. This is refrigerating effect. This is joules per kg, and this one is joules per second, kilowatts, or will be expressed as tons of refrigeration. And 1 ton of refrigeration is 3.52 kilowatts. This is given by mass flow rate of refrigerant multiplied by RE. Is given by H1 minus H4. COP of a refrigerator is either W dot, either RC divided by W dot, or if m dot is same, then is H1 minus H4, that is RE, divided by specific work is H2 minus H1. If a compressor has a certain mechanical efficiency, then you divide this by mechanical efficiency if given in the numerical. Otherwise, assume 100%. The number of times the question asked is that how much mass flow rate is handled at this point. So what is the mass flow rate at this point? Is it m dot? And can we write m dot equals to density multiplied by volumetric flow? This one is volumetric, is meter cube per second, and is normally the sweat volume of this one expressed in meter cube per second. And density was normally done as a reciprocal of specific. So flow rate is m dot divided by rho, or m dot multiplied by specific volume at inlet to the compressor is V1. Inlet to the compressor as per this figure is dry and saturated, so value of V1 is taken as VG at evaporator pressure. Normally TS graph is not used for vapor compression because we have two constant pressure process and one isoenthalpic process. So preferred graph is pressure versus enthalpy graph. The pressure enthalpy graph is shown by this one. This one is a dome. This one is critical point. This is saturate liquid line. This one is saturate vapor line. Vertical line represents isoenthalpy. Horizontal line represents constant pressure line. And the temperature line will go like this. This one is also constant temperature line. Isoenthalpic line will be vertical and constant pressure will be horizontal. And this side we have isentropic lines. Isentropic lines are like this. So we have isentropic process represented this way, isothermal represented this way, constant pressure is also represented same way, isoenthalpic is represented by vertical.